Hello everyone. We have came here for the organic chemistry, same three, the next chapter, the polynuclear hydrocarbons. The polynuclear hydrocarbons. We will know the definition of the polynuclear hydrocarbon first. When two or more benzene rings are fused together, then it is formed a fused ring, a polycyclic ring, or polynuclear hydrocarbons. They are basically formed due to the incomplete combustion of the organic matter. Naphthalene is the simplest form of the polynuclear hydrocarbon. So we have taken here the naphthalene for the general and the simplest form of the polynuclear hydrocarbon. We will focus on the synthesis, the resonance part of the polynuclear hydrocarbon, and the substitution or reaction of the naphthalene. First, we see the aromatic character of naphthalene, anthracene, and phenanthrene. The resonance energy of the cycle of the benzene ring A is 61 kcal mole minus 1. Resonance energy of B is 84 kilocalorie mole minus 1. Resonance energy of C is 92 kilocalorie mole minus 1. And the basic resonance energy of benzene is much less, that is a 36. But when they fuse together, then the resonance energy goes on increasing. Now the resonance structure and the bond length of the depend upon a formula. That is, if there are n plus 1 number of principal resonance structure for polynuclear aromatic hydrocarbon, that is, a n signifies the number of benzene rings which will fuse together in the linear matter, not in the angular matter. So the double bond character, the bond length, the different carbon-carbon bond length reveals a decreased aromaticity of fused polynuclear hydrocarbons, and phenanthrene is an angular polynuclear aromatic hydrocarbon. We will come to phenanthrene in the next part of the chapter. So first consider the naphthalene, that we can see that there is two benzene ring, that n equal to 2. That's why it has a resonating structure of 3. Now we see the anthracene. We can see that is a 3 benzene rings are being fused together. That is a n equal to 3. That's why we can have that n plus 1 number of resonance structure. That is a 4 resonance structure. 4 resonance structure. Now we see the phenanthrene. Since it is angular, that's why it doesn't follow the rule. It has 5 resonating structure. The naphthalene naming, we start off from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9, 10 is a fused part. Now we can see the nomenclature. That is, if it's substituted at one position, we can consider it as alpha. And if it is substituted at 2 position, we consider it to be as beta. Now as special names at alpha naphthal, that is alpha naphthalamine, that is a 1 position, the alpha naphthalene sulfonic acid. Now we see the synthesis from petroleum extractor with copper at 680 degrees centigrade. When we reach 4-phenyl 1-butene is being passed over red hot calcium oxide to form the naphthalene with the release of hydrogen. The naphthalene can be also being synthesized from the 4-phenyl 3-butanoic acid. We can see the resulting structure as naphthalene and the release of an zinc oxide. We can also synthesize naphthalene, which is a very important synthesis, the Howard synthesis. You can see the steps, there is the interarrangement to form the naphthalene. I have given you the slides over the classroom. You can just have a screenshot, or you can also take the screenshot from here to have a detailed note for yours for the synthesis purpose. And the petroleum also, it can be synthesized. I have given here the synthesis from petroleum also. That is, we can see the normal butanoic acid, the Howard synthesis, and from petroleum. The 3 methods for the synthesis of naphthalene. Now the naphthalene reactions. The first and foremost is the oxidation with the chromium oxide. If we react, we form that 1,4-naphthoquinoline, where the 2 double bond with the 2 oxygen has been added. If we react with oxygen V2O5, the phthalic anhydride can be formed. At 460 degree, to 480 degrees centigrade, which is a most serious step. Now, because naphthalene is very sensitive to oxidation, you cannot make naphthoic acid by oxidation of a side chain. This is the two reactions which correspondingly provide the corresponding product, naphthanoic acid. Now the reduction comes here. If we react with sodium and ethyl alcohol, then the corresponding product will form 1,4-dihydronaphthalene, then the tetrahydronaphthalene, that is we basically call as tetraline, and the decalene if we react with platinum and hydrogen with increased heat and pressure. Now the substitution is very important, that the two principles has to be followed. One is the number of resonance structure and the aromatic sextet principle, which basically follows the substitution reaction, but the substitution at one position is more stable due to number of resonating structure than the two position. So we will see the substitution reactions over here. The electrophilic aromatic substitution, nitration. If we react with HNO3, the NO2 getting being attached, the nitrogen dioxide, the sulfonation, we can see that one position, but at extreme temperature, that 160 degrees centigrade, we get the HSO3 giving attached at the two position. Halogenation, no catalyst has been required. The bromination we have seen here. The electrophilic aromatic substitution, that Friedel-Crafts alkylation can also be done with the reagent of CaCO(Cl) and AlCl3 with a non-polar solvent, and the nitrobenzene, we can see the same reaction is being carried forward. Very sorry. Now we can see the electrophilic aromatic substitution in the synthesis of substituted naphthalenes. With the naphthalene react with bromine, the corresponding bromine has been attached, then the Grignard reagent has been forming, then we are being attached with an NH2, then we reduce it, the NH2 to nitro group, then we can again produce the same product of naphthalene. This is the two steps which can follow up our electrophilic substitution reactions, and we have given here a summary of the total naphthalene reaction. This is all about of the naphthalene. Our coming week will follow up with the naphthalene chapter. Thank you.